Okay, so we get to talk about mean value theorem, and along with that comes a little bit of discussion about average rate of change versus instantaneous rate of change, and also a little bit about interlacing zeros. So let's start with the mean value theorem. Okay, first I'm going to write it more or less the way I think about it. First of all, if f is continuous on a closed interval and differentiable on the open interval, then there's some value in the interval, like on the x-axis, the independent variable axis, such that the instantaneous rate of change at that point has to equal the average rate of change over that interval. That's like saying if you're running along a track and your average rate of change is you're running on average 3 miles an hour, then at some point you had to be running 3 miles an hour. Maybe you ran a little faster and a little slower. Now with human beings that doesn't necessarily work, because maybe you're going 2 miles an hour and all of a sudden you start going 7 miles an hour. I mean, you don't have to make that, it doesn't have to be continuous. You can jump or it can be non-differentiable for a human. Let me show you why we need all these conditions. Let me tear this apart one piece at a time. Okay, so if we have, this is your standard situation here, where you just say, okay, maybe here's A, and let's say here's B, and here's F, and it's continuous all over, and it's differentiable. Notice that it has to be both continuous and differentiable. But there's that deal about whether or not you're on the open or closed interval, okay? So it means that if you have this average rate of change, which is the slope of the secant line between those 2 points, that's what that means. It means it's your average rate of change. Then what you can do is you can take this line, unfortunately I've got the points along with it, I can slide it until that line is tangent to the curve. And it could happen at more than one place, but it's guaranteed to happen at least one place. And it's actually pretty much a direct result of the intermediate value theorem, but this is sort of intuitive all by itself, so we don't really have to even refer to that other theorem if we don't want to. So let's tear this apart a little bit. Why do we not just say continuous? Why does it have to be differentiable? Well, give why. Okay, this function is continuous but not differentiable. And then if we take and give ourselves a secant line, and then we try to move that secant line around to see where that curve matches that slope, it's not going to happen. Just not happening. We try to go here. It's not differentiable there, so that doesn't even make sense. But that's the closest match. But the problem is, if you wanted to define a secant, if you wanted to define a tangent line here, you'd have to define all these possible line segments as being tangent lines as you transition from one valid tangent line to another. So there you go. Or you might even fill in all these guys here. It depends how you're going to define your tangent line. Anyway, there's too much confusion. So we just say it's not differentiable there. We're not going to have a tangent line there, and so this isn't going to work. So this thing is a no-go. We don't accept that kind of logic. Okay, so we should talk about what the way we usually see this written, like in a textbook or something. We would say f prime of c, so that's the instantaneous rate of change, is equal to the average rate of change over that interval. So here we have b, f of b, here we have a, f of a, and whatever this slope is, we're thinking along the lines of, gee, this is going to match like right about there. Then this guy is going to be c, and this is going to have a derivative it is actually kind of close to 0, maybe slightly positive. But that's what that means. We're saying that we can find a point somewhere between a and b We're not allowing the endpoints here. It has to be between A and B, and it's going to have a slope. This tangent line is going to have the same slope as the secant line did. So that's what that means. Okay, so here's a question. Let's say we have this curve and we want to know what is the average rate of change from 0 to 4. So you can have a graph and you're asked for the average rate of change. So you want f of b minus f of a over b minus a. Well, let this be a, let this one be b, and it's totally okay if you flip them, but you're just going to confuse yourself, so don't flip them. All right, then you're going to say, all right, f of b is 2, f of a is 3, b is 4, a is 0, is going to be negative 1/4. So if you think about this, this is what your tangent line is going to look, your secant line rather, is going to look like. And so you may have another question. You may have another question that says not only what is the average rate of change, find me a point where, find me a point between A and B where the slope of the tangent line seems to match most closely. And actually it's going to be probably somewhere around here or here. Not in the middle, not on the ends. In this case, because if you zoom in on this, it kind of looks like an S shape, right? It kind of looks like that if you zoom way in. So right in the middle, it's not going to be perfect, so don't pick the middle. So if you were asked to guess a C value, C is approximately 1 or C is approximately 3, to be that point at which the tangent line slope is going to match the secant line slope. That's not to say that's always true. So what if A is over here, right? What if A is over at negative 3? We're going to ask that same series of questions. Then the slope is obviously 0. Slope of the tangent line is 0, and then we want to know where is that going to happen, and that's going to happen close to 0. So in that case, C is equal to 0, meaning this 0 here is lining up with where we have a horizontal tangent line. And so in that case, you'd say f of b minus f of a over b minus a is going to be, well, whatever it is, 2 minus 2 over 4 minus negative 3. It doesn't matter as long as the numerator is 0. Then you just find another point with a horizontal tangent line. Okay, and last but not least, we want to talk about interlacing zeros. And so what we're going to do here is we're going to say what happens if we have a function. And, you know, I guess I'll just put the axis in for fun. The axis doesn't really matter for this question. The y-axis doesn't matter. It's the x-axis we care about. We're just looking at how many times you get zeros in this function. And the trick we're using here is between each pair of zeros, then the derivative is going to somewhere have a 0. Okay, and that's based on the theorem we just did. That's mean value theorem says if you have two zeros, like here's my first 0 and here's my second 0, so I'm going to let this be A and let this be B, and according to the mean value theorem, somewhere between A and B, maybe more than one place, so it could be more, but a minimum of one of these points between A and B has to have a 0 derivative. So we get this set of interlacing zeros. Again, there's nothing saying we can't have more zeros in there, but we have a minimum number of zeros. So if the original function had 1, 2, 3, 4, 5, 6 zeros, then the derivative has to have at least 5 zeros. Now, how could there be more? Well, let me show you. This is not that hard to do. We see these kind of functions all the time in calculus class. We have only 2 zeros, right? And so this guy over here is essentially the 0 that we're guaranteed by the theorem, more or less. But we get some additional zeros in the derivative. So the red tells me where the derivative is 0, and the blue is telling me where the function is 0. But we are only guaranteed 1. They can come in, we can get additional 1s in sets of 2, right? So this can easily happen. So you can get more zeros, but you can't get rid of zeros that way. Okay, and that's all you need to get through worksheet 20. I'll see you in class.